And I'd like to thank the organizers for the amazing idea to have this conference and for the very efficient organization too. So that's a good point. Okay, so I will try to give a not too technical talk. So my aim is rather to do some publicity to this area. Okay, and I'll start with, well, as I said in the abstract, this is all joint work with Jonathan Harpas. Okay, so after wonderful talks by Olivier, you may be left with the impression that many results are accessible for rationally connected varieties, which of course has been the focus of much work on rational points. So I would like to somehow try to counterbalance this point by maybe advocating the point of view that there's life sort of beyond the world of rationally connected. So there's some hope to get results for varieties which are not rationally connected. And so the focus of this talk is K-free surfaces. So X is a K-free surface when it's smooth projective and has this cohomology with coefficients in the structure sheaf O. So we are our field, which will very soon become a number field. So it's say characteristic 0, and examples of K-free surfaces are well known. So for example, quartics in P3, intersection of a quadric and a cubic in P4, and also I'll talk a little bit about intersection of complete intersection, smooth complete intersection of three quadrics in P5, and also Kuma surfaces, which I'll talk about more in a second. So what's the hope of actually being able to do something when we leave the sort of more or less understood world of rationally connected varieties and venturing to something beyond? So the hope is that we are getting closer to the other important object, which is abelian varieties. So abelian varieties are, of course, very well studied, so we know a lot about abelian varieties. So hopefully K-free surfaces are not completely inaccessible, because there are some links with abelian varieties. So there is a construction due to Kuga-Satake that has been derived by deem. I'll just mention this very briefly for completeness, which attaches to a K-free surface a certain abelian variety of large dimension that, as deem has showed, is defined, so we are in characteristic 0, is defined over some finite extension of the ground field. So that has been used by Yuri Zark and myself to prove that, well, of course, the fundamental ingredient of that proof is the celebrated result of Faltings about the Tate conjecture for abelian varieties. So as a consequence of this, we proved that something that Rachel mentioned in her talk, that this is finite when X is an abelian variety of any dimension over a field which is a number field or finitely generated over a parameter field, or a K-free surface. So for K-free surface, I can put 0 here. So right. So basically, I have a number field, but the result more generally says that you you also have the same finiteness if your field is just finitely generated of a Q. And more recently, we've generalized this using some fundamental work by Medope-Poussepere on the Tate conjecture and so on. Some really hard work. So this was just a remark that the basically same idea establishes this result for characteristic P different from 2. So all right. So maybe that's just one illustration that you can really use the connection with abelian varieties to prove something for K-free surfaces. But you can do more if your K-free surface is a Kummer surface. So in this talk, I will talk about Kummer surfaces. And of course, right. So from now on, K will be a number field, and let me spend 2 minutes talking about the conjecture that rational points of K-free surfaces are controlled by the Brauer-Manin obstruction. So that's something we've seen in a number of talks in this conference. So X is a K-free surface. So of course it's a very bold conjecture because the evidence is not as substantial as we would like it to be. So there is some evidence. So there are some conditional results due to Collet-Lenz and also myself, based on Schinzel hypothesis and the conjecture that SHA should be finite for elliptic curves of number fields. So that proves the existence of the existence part of this result. I mean, it proves that the Brauer-Manin obstruction is an obstruction to the Hasse principle for a large family of elliptic K-free surfaces that can be written as fibration in elliptic curve. So there's some theoretical evidence, but also numerical evidence. Okay, so some conditional results, and also numerical evidence. So there are calculations, for example, by Elsen, Hans, and Janel for Kummer surfaces where they check weak approximation. So they look at local points and they just search for rational points that approximate them somehow. So everything seems to be working fine so far. But apart from this, I'd like also to mention results about Zariski density due to Logan, McKinnon, and van Looyk, and results about periodic density due to Swinton, and Pannekoek. So far, these are kind of isolated examples of K-free surfaces for which rational points are dense in periodic points for one given prime number P for some, or I think René can do also 2 primes, but I think not much beyond that, unfortunately. So evidence is scant. So and all the evidence, I guess, is for surfaces which have a pencil elliptic curve. So maybe it would be more appropriate to state this conjecture for K-free surfaces with a pencil of curves genus 1 on it. So I don't know. But anyway, so I heard it from at least one colleague that who referred to this conjecture as a dogma. So I guess the difference between the conjecture and the dogma is the conjecture. So it's something which you think should be true because there's so much evidence, and dogma is something which you're sort of rather tend to believe in because you don't have anything else to believe into. Okay, so anyway, so I think it's okay. Anyway, so but there are also other things why rational points on K-free surfaces, in particular Kummer surfaces, are interesting. Let me mention just one result by Holmes and Pannekoek. which I think should be somehow better known, they link to important conjectures, the conjecture of this kind, but not just for K-field surfaces, but for slightly different class of varieties, and the question about the rank of abelian varieties in families of quadratic twists. So what they prove is that if the Brownian abstraction to weak approximation, so which means the full strength of this statement is controls rational points on not the Kummer surface, but Kummer variety of perhaps larger dimension for a power of abelian variety A. So let A be an abelian variety, look at R power of A, and then do the usual thing. So this is just the minimum disangularization of the quotient of this power of A by the antipodal evolution iota. So that's a standard thing, except that the dimension is not necessarily 2. Okay, so if the Brownian abstraction to weak approximation controls rational points on such a Kummer variety, then A has a quadratic twist of rank R. Okay? And therefore, if we are very courageous and we believe in that the same thing should hold for Kummer varieties of any dimension, then for any given abelian variety over a given number field, we can find a quadratic twist of arbitrarily high rank. And this is probably not a common belief these days. Well, I'm not quite sure. Well, anyway, this is this shows that this is a very hard question anyway. So. Okay, so there are links to interesting results about interesting questions about abelian varieties. So maybe this is something worth looking at. Okay, and now let me state the main result.
For any A or for a specific A?
Any A. Take any abelian variety over any number field, and then that's true. And the construction is completely elementary, so it's basically a clever trick. So. Well, that's the end of the introduction. So let me state 2 theorems, which will be, in fact, which will look slightly different, but will be both. So each of these theorems is a result about a certain class of Kummer surfaces. So here's theorem A. So as I said, K is going to be a number field. And let g1 of x, g2 of x be 2 polynomials of degree 4 with Geller group S4. So generic case. So each of them has Geller group, the maximal possible Geller group, symmetry group in 4 letters. Right, so let's assume there's a technical assumption. Assume that we have 2 places so K has 2 odd places W1, W2, not equal to each other, such that my polynomials have integral coefficients at these places. And discriminant of the first polynomial at W1 is the information parameter, and discriminant of the second one at W1 is a unit, and vice versa. So in other words, the valuation at Wi of the discriminant of Gj is Kroneker's delta. Okay, this is again a generic condition. And finally, I would like to assume, so the conjecture that gaining more and more evidence, that the Tate-Shafarevich group of EI C has finite two primary part where so EI C is the Jacobian of the curve Okay, so this is the curve of genus 1, and this little c is non-zero element of k. So I'm doing quadratic twists, and so I'm assuming the finiteness of Shah for very many elliptic curves somehow here. And then the conclusion is that smooth projective models of the variety with the affine equation z squared equals g1 of x, g2 of y satisfy the Hasse principle. Right, so there's no Brouwer group, and as long as I have points everywhere locally, there's also a global point. That's the statement. Now let me explain, okay, so some of these assumptions are generic. So by the theorem, I think it was van der Waarden who remarked that, so if you have a random polynomial, it will have the maximal possible Galois group, that's okay. And then this condition should hold for maybe for 100% of curves. I didn't check this, but a very easy Sieve argument shows that there's a positive proportion of, so you can do it, for example, of integers, of usual integers, just positive proportion of pairs of such polynomials will satisfy this condition. That's no big deal. And then, of course, this is massive assumption about finiteness of Shah, and that's enough. So the reason there's no Brouwer group is that this condition just imply that the relevant part of the Brouwer group is 0. I'll mention this when I sketch the proof a little bit. And so finally, I guess these days, after results of Bargova, Skinner, Weijang, we have finiteness of Shah for a positive proportion of all elliptic curves. So maybe that's so we're getting closer to somehow replace this by something unconditional, but there's still a long way to go because it's just 2 is the experts explained to me that 2 is the hardest prime somehow as far as finiteness of Shah is concerned. So anyway, and of course. So if you wonder why this equation, so this is a Kummer surface, in fact. So smooth projective model of this affine surface is a Kummer surface attached to the product of two curves of genus 1, which are C1 and C2. So Ci is precisely the curve with this equation where I is 1 and 2. So the involution on Ci changes the sign of y and does nothing to x. And so this is iota that acts simultaneously on both sides. So when I mod out by iota and I resolve singularity, so this tilde means the singularity is resolved, then that's a Kummer surface. So this is theorem 1. Now, theorem 2 is similar, except it applies not to abelian surfaces which are products of two elliptic curves, which is somehow the case here, but to the Jacobian of a curve of genus 2. So again, you can give explicit equations for the varieties to which theorem B will apply. So notations for theorem B are as follows. So f of x is a monic, irreducible polynomial of degree 5. So you will immediately point out that I'm talking about hyperelliptic genus 2 curves with one rational Weierstrass point. We weren't able to deal with the general case somehow. So that's a bit simpler. And okay, L is going to be the field extension of degree 5 attached to this polynomial. Theta is the image. Theta is an element of L, which is the image of X. A is the Jacobian of C, where C is the curve with this equation. And finally, I mentioned that, well, as usual, perhaps I should mention the work by, well, the people worked a lot with two coverings of A in this situation. So such a two covering is given by a torsor. So any torsor for the finite group scheme, which is two torsion of A, is given by so I fix a non-zero element in L, call it lambda, and then I look at this equation inside. So I look at, basically, I'm extracting square roots of lambda in the quotient by plus minus 1 of the restriction of scalars of GM. So because I'm doing this quotient, I get exactly the right kind of the right size of. Anyway, so with this notation, I can give the Kummer surface associated to a two covering of A corresponding to lambda by explicit equations as a complete intersection of three quadrics in P5. So I can write down these equations. So x lambda is going to be the following K3 surface. So here's so P5 is obtained. So it's convenient for me to write it down as the projective space associated to the six-dimensional affine space, which is direct sum of two, if you like, two vector spaces. Well, okay, so this is a five-dimensional piece. This is a one-dimensional piece, and I'll use I'll write the coordinate here. So this is the coordinate that takes values in L. So L variable. So this will be the coordinate here, and then U naught is just a usual K variable, which is a coordinate in this affine line. And with this equation, so with this notation, X is given by these three quadrics. So that's not a big deal to write this down. Somehow it's just basically reworking of Lagrange interpolation. I mean, it's the classical stuff. So this should be 0, this should be 0, and then this is 0 too. So these are three quadrics. U naught appears only in the last one. So this is I mean, you can check this is a smooth K-free surface, smooth surface for three quadrics in P5. Okay, and the statement is, so theorem B finally says that. Oh, maybe I should continue on the board. That under some condition, this surface satisfies the Hasse principle. So I need some technical conditions similarly to theorem A. So assume there exists a naught prime W such that my polynomial has integer coefficients and again the discriminant is a uniformizing parameter. Now, similarly, I'll have to assume that psi is finite. And again, this is required for the two primary part of the Tate-Schaffer group of basically any quadratic twist of A, Jacobian of C. Okay, so let me not write down that this notation stands for quadratic twist of A. And then for lambda in L star such that there exists an R in K star for which the valuation of the product R lambda is even at all primes of L above W. So that's a rather annoying condition, but it's got to be there. Okay, this is unfortunately I can't prove result for an arbitrary value of lambda, which I would like to. So there's a certain restriction. Well, it's not too bad somehow. Anyway, so this says that okay, I must have an element. So up to modifying my lambda by something coming from downstairs from the ground field, I have even valuation at all primes above the prime W mentioned here. So the conclusion says that x lambda satisfies the Hasse principle.
You have no condition on the Galois group of that?
Oh, I do apologize. Yes, I do have. Well, actually, what I said is correct. Now, but this is entirely a reasonable question, which I will address in a second. Just one last thing, which I forgot to mention, theorem A. So we, basically by the same proof shows that rational points here are Zariski dense. So we're not again a Hasse principle, but x of k is Zariski dense in X. And there's a similar supplement to theorem B, but this will work for lambdas for which this is not a trivial torsor. So if this torsor is trivial, then I can't prove the Zariski density, but so basically the condition is if lambda is not an element of k star L star squared. If it is, then this is trivially satisfied. So if you exclude those trivial examples of lambda, then we get the Zariski density. By the same method. Now, let me address Philippe's question. So if you look at possible Galois groups of this polynomial, okay, there's a range of possibilities, but because I'm postulating here the existence of this prime W with this condition, it severely restricts the possibilities. And somehow it does turn out that the Galois group is S5, but it just follows from other assumptions. Okay? Now, if you've never seen these equations so again, the geometry of the variety in question is that x lambda is cum of y lambda, where y lambda is a two covering of A. So in other words, there's a map y lambda to A, which is passing to the quotient by the action of translations of two division points of A. And so this is the two covering given by the class given by lambda. So lambda is you can interpret lambda as providing you with the class of this torsor is an element in H1k with coefficient into torsion, and if you're twist by corresponding cocycle, you twist A by the corresponding cocycle, you obtain y lambda. Because the class of y lambda is of order 2, it is acted on by the antipodal involution just as well as A's. And so we can form the associated Kuma surface. Now, if you don't want a smooth Kuma surface, and if you are a kind of a traditionalist geometer, you may be happier to work with the quartic in P3, right? And this is indeed possible. So there's a map from x lambda into P3, which contracts the 16 lines to singular points, and the singular locus is precisely this the torsor for this finite group scheme I have 2. So the 16 points are, form one Galois orbit, of course, and that's a torsor by which we twist A to obtain y lambda. Okay, so there's many ways of looking at this X explicitly. So basically, this theorem look completely different, but they are just instances of the same more general result, which I don't want to state because it's a bit technical. What I would like to do now is to explain how these things can be proved. And the idea is, actually, it's got a very brilliant idea that was found by Swinnett and Dyer. And it seems to me that, in some sense, this is the only way of actually producing rational points on K-free surfaces that we are aware. So, of course, if your K-free surface has an elliptic fibration, you can use, that's the other well-known trick. You can use the elliptic curves to create more points. If you have one point, you can create more, and then if you have several fibrations, you can go on like this. But you need to start somewhere, okay? If your surface doesn't have an obvious rational point, maybe no rational points at all, so where do you get them? So you must have some mechanism for creating rational points. And so here's a here's the idea of the proof. And as I said, it goes back to Swinton-Dyer. So it's a really, really, really clever idea, but it's somewhat crazy and doesn't always work. And I'll explain its limitations after I explain the idea. So the first observation. So okay. So the general situation is: so suppose we have an abelian variety A2 covering Y, and the associated, say, Kuma variety X. Then you cannot recover A from X. What you can do is you recover A up to quadratic twist. So if you take any non-zero element of K and let AC be the quadratic twist, of A by C by the quadratic extension of K obtained by adjoining square root of C, then X is going to be, so same X is obtained as a Kuma variety associated to the quadratic twist of Y. Now, okay, because the translations by points of order 2 and multiplication by -1 commute, so what I'm saying makes sense. So I can simultaneously twist Y and A by the same element C, and everything will work just as it worked before. So I'm not able, in other words, I'm not able to distinguish between quadratic twists of Y. And quadratic twist of Y is a 2 covering of quadratic twist of A. So philosophically, somehow you have to look at all quadratic twists. They're all equal. Now, let's suppose that we're given a class so alpha is some element in this cohomology group, so Galois cohomology of coefficients into torsion. And we use, so assume that, well, we're not assuming anything, we're just, Y is the 2 covering obtained by twisting A by alpha. So just don't get confused, because I'm talking about quadratic twist. Now this refers to the action of Z mod 2, which is just sends x to minus x. There's another action, there's another twist in the story, I mean, which is a twist when the subgroup of 2 torsion of A acts on A by translations, and we have this class alpha, and so we twist A by this class with respect to this action, so we obtain Y. Okay? So somehow these two things operate independently of each other, quadratic twist and twist by this class. Okay? So the method works as follows. So there's step 1, which is an instance of vibration method. Actually, something which was mentioned by Olivier. So use vibration method. Method to get some elements in T such that the quadratic twist of Y by T is everywhere locally soluble. Okay? Now, geometrically, because we're used to looking at pictures, so one way of doing this is just look at this curly Y, which is a threefold obtained by passing to the quotient of y cross P1 by an involution which acts as iota, the antipodal involution on y, and plus minus 1 on P1. So by plus minus 1, I mean that we fix the coordinate t. Well, t is not a, okay. X is a coordinate on P1. So P1 is a fine line plus infinity. So we remove 0, 2. So we have GM. And so if X is a coordinate on GM, then the map that multiplies X by minus 1 is an involution. It has two fixed points, 0 and infinity. So when you do this quotient, you obtain some threefold, which will be, which will have the map to P1 with two bed fibers at 0 and infinity. So it's like an isotrivial kind of thing, which after fine extension of the base splits into a product. But anyway, the point is that away from 0 and infinity, the fibers of this map are precisely so yt. So if I call this pi, then so if t is not equal to 0 or infinity, then the fibers of this map are precisely quadratic twists. So we get a family of all quadratic twists, and then we also have some bed fiber at 0 and infinity. But in this situation, when only two fibers are degenerate, the fibrational method is well known. Now, the fibers are not rationally connected, of course, but it plays no role, because all I want is a fiber which is every locally soluble. And this is possible due to, I mean, this, for example, this was proved by Collatin and myself. So there's some, I mean, by now I suppose it's a very easy, almost baby. I mean, an adolescent version of fibration method. Okay, so that's the first step. Now, why is this helpful? Well, of course, this is an approximation. So what we're really after is quadratic twist of y, which has a k point. Because if we have a k point, as I explained it somewhere before, that, yes, I explained it here. So X is a Kuma variety associated to any quadratic twist of y. So if we have one quadratic twist with a rational point, we are home. But so it's a good approximation, it's a good start. And then step 2. Step 2 is a place where you really have to work hard.
Here
Sorry?
you're using the hypothesis that, so you want to prove this satisfies the Hasse principle. So you're assuming that the thing has points locally.
Absolutely. Yeah. I mean, I'm assuming that X has points locally. So if X has points locally, then what did I say? Yeah, then this thing will have points locally because okay, so if X has points over locally, then this curly Y has points over locally. And the reason for this is you just do argument at each parameter, at each place of k independently. So for any given place, okay, so any point in the Kuma variety lifts to a rational point on some quadratic twist, and that's why. Good. So step 2 is the place where actually you have to do work, you have to do some serious work, and maybe before I describe step 2, let me just reformulate the outcome of step 1. So what have we got? We've got a torso, a principal homogeneous space for A, which has points over locally. Now, this means exactly so that so yt is ever locally soluble it's the same thing. It's just a different language. That to say that alpha is in the Selma group, in the 2 Selma group of the twist of A by the same element T. Okay, that's just basically the definition of a Selma group. Selma group, 2 Selma group. So let me just remind you that. So recall that cell 2 of A is a subset of H1 K A2, consisting of the classes that create every locally soluble torsors for A, corresponding to so I'm just normally Selma group is defined in terms of exact sequences, and we've seen this. We're going to see this definition in a second. So that's the formulation of the outcome of step 1. And so the step 2. So we aim to, while preserving the condition that Yt is ever locally soluble, at the same time try to arrange that the Selma group is very small. Okay, so here's step 2. So keep the condition that Yt is ever locally soluble. Arrange that at the dimension as a F2 vector space of Selma 2 of AC minus the dimension of rational, so the space of rational points of order 2 is 1. Okay, so maybe I need to be a bit more precise, but that's the essence of what we're trying to achieve here. Now, the reason why this is useful, so suppose we can find such a quadratic twist. And then recall the standard exact sequence that relates the Selma group and the Tate-Schaffer-H group. So there's this, basically by definition we have this map, and the kernel is the image of rational points. Now, in theorem A and theorem B, I mean, this part doesn't really exist because the polynomials are such that the Galois group is very large, as large as possible, so this actually disappears. So we can, for the sake of this, let me just for simplicity, just ignore this bit. This is 0 in all cases. And then what we're trying to achieve is that just to make the rank of Selma equal 1. Now, the rank of Selma equal 1 actually means in my situation that this group is just, as I said, this is 0 and alpha. So from the very beginning, I'm assuming that alpha is not 0. Well, I didn't say this, but considering 0, alpha, which is 0, is not somehow interesting because we're not getting interesting the Hasse principle. So, right, so from the very beginning, I make this assumption. And then if the Selma rank is 1, then this is just what I have. So this is Z mod 2 is a group. And then we have the alternative. So alpha can go to 0 here, in which case we win, because if alpha goes to 0, then SHA is subset of H1 KAT. So the group that classifies the torsors for AT. So if alpha goes to 0 there, it means that it means that yt has a rational point, and that's exactly what we want. Because yt is precisely the torsor for at given by alpha. The other possibility is that when it does not go to 0, but then the size of this group will be 2. So if alpha does not go to 0, if alpha goes to something non-zero, then this is isomorphic to z mod 2. And we know that, for example, for elliptic curves, this is impossible due to a result by Castles or Tate. So it's at this point we use the massive conjecture that psi is finite, our two-primary part is finite, because this implies, by the work of Castles and Tate, that if A was an elliptic curve, then there is a pairing, there's a alternating pairing on this group which is non-degenerate. And it's well known that this implies that the size of this group must be a square. So it cannot be equal to 2. So in fact, the second possibility can never occur. Now, I'm also talking about more general abelian varieties, so I need to be more precise here. But fortunately, we have the work of Poonen and Stoll, and also work of Poonen and Reins, and the result of our research. So theoretically, there existed examples of abelian varieties for which this group has order 2, but it's not happening in this situation of theorems A and theorem B. So we're talking about principally polarized abelian varieties for which principal polarization can be factored in. So we have to create some form and then use Poonen and Stoll's results. We can show that everything works as in the case of elliptic curves. So this is one of the reasons why looking at hyperelliptic curves, I mean, it's most general hyperelliptic of genus 2 without Weierstrass rational Weierstrass is going to be a bit tricky because you have to deal with this thing. That will be a problem here. Anyway, so that's how it works. And as I said, this is a very pretty idea, but unfortunately it doesn't always work. And it doesn't always work for at least 2 reasons. There are examples of elliptic curves that have no quadratic twist of Selmer rank 1. Okay, Selmer rank should be, now in general situation when we're talking about elliptic curves that possibly have have rational two torsion points, then we have to look at this sort of modified Selmer rank, by which I mean that we subtract this from this. Okay, and it can't always be achieved. So there are at least 2 reasons. So Tim and Vladimir Dokshitzer proved that over some fields, the parity of the Selmer rank is constant for all quadratic twists. Well, this will never happen for rational numbers, but because the theorem says that this can happen if and only if the field is totally imaginary, and the elliptic curve requires good reduction over some abelian extension. There's a precise statement when this happens. So that's one possibility. But there's even a more dramatic reason why this method doesn't work sometimes, which was given by Zev Klugsburn. So he proved that over any number field, so again, I think these results should be better known, so maybe I just spend a little bit of time talking about this. So over any number field, capital K, there are elliptic curves with a lower bound on the Selmer rank, such that elliptic curves E, such that this modified Selmer rank or reduced Selmer rank or whatever has a lower bound, which is number of complex places of K. Again, this is it's nothing threatening us of a Q, but anyway, somehow, I mean, we should be aware that this phenomenon occurs. and this is proved by the explicit example somehow. So he comes up with an explicit family of these curves. So these curves have a rational point of order 2, which is not entirely obvious from the equation. So, so this is a rational point. So okay, so if I call this E, maybe En, and then these curves are defined over Q, but you can adopt this N. You can choose the appropriate N, so that over K, this curve would create an instance of this phenomenon somehow. Namely, the condition is that if so n is going to be a natural number, and take n such that this is not a square. Okay, you can do this, and so, and then for these curves, then this lower bound works. Okay, so that's not, of course, the general case. So last 3 minutes of my talk, maybe I'll just mention what other questions are related to this. So now, first of all, there's this massive activity. There's a series of papers by Maser, Rubin, and also by Maser, Rubin, and Klugsbrunn, where they study the distribution of Selmer ranks and families of quadratic twists. So in some cases, I mean, this is all a continuation of the work by earlier work by Hugh Brown and also Swinton Dyer. So they prove in some cases that there's a distribution, there's a probability distribution, there's some of Selmer ranks in the families of quadratic twists as I studied here, but because of these counterexamples, and so in a situation when this applies, there is no distribution. Okay, so I don't think people understand what's going on really somehow. So what exactly is at work here? Why sometimes you have a distribution, sometimes you don't? For example, if you have just one elliptic curve such that the Galois image is S3, then there is a distribution. So this is the result of Maser and Rubin. And also there is such a distribution if the two torsion is entirely rational. But in this case, when you have just one rational point, things can break down. So finally, I'd like to mention that perhaps this case is very special. So there's ongoing work, which is, I mean, as usual, so anyway, so I have some emails from Jonathan Harpas where he shows that you can impose conditions like in theorem A and theorem B, such that even in the case when you have one rational point, one rational point for the two, you can still prove results as similar to theorem A and theorem B. One other thing I would like to mention is that the immediate predecessor of this work was my paper Swinton Dyer, which was published 10 years ago, which gave something similar for Kumi surfaces attached to products to elliptic curves with full rational torsion. So with trivial action of Galois group on points of order 2. But that paper was very, very complicated because at that time, this idea of Swinton Dyer was, somehow the step 2. So we had to use the so-called symmetrization machinery, like in Olivier's thesis and some other papers with Collet-Allen, which is extremely heavy to use. Now, the advantage of this work with the entire path, theorem A and theorem B, is that there's no need for this symmetry machine anymore. Somehow, this interaction with the ideas of Mason and Rubin made it possible to use rather much more natural devices somehow to achieve. So prove this theorem is not hard at all. I mean, if I had an entire lecture at my disposal, I could easily describe it somehow in full detail. So somehow it's easy now. So and then also I got an email from Harpas that says that the paper that the results we proved with Swinton Dyer can now be reproved using this much more natural machinery, using the ideas of Mason and Rubin. So both in the case when this is entirely rational, and in the case where there's just one rational point, I mean, these conditions are ruled out by assumptions of theorem A and B. So in these cases, there's still the thing seems to be working pretty nicely. So anyway, somehow the point of this lecture was to advertise this technique, which again seems to be the only way. Well, the drawback is, of course, it's conditional on this massive assumption that psi is finite, but maybe this will be removed in 10 years' time. Let's be optimistic. And so it seems to be the only trick, which is strange now because of this. I mean, we're not hoping for this trick to work always, but we don't have other tricks. So maybe now things get much nicer, and maybe it's time that maybe so if somebody else would want to look into this stuff, I mean, I'll be very happy. Anyway, let me stop now. Thank you.